I did.
No, I got the
It went down.
Alright guys, let's take a look at page 349. We're going to deal with these properties a little bit more until we start to talk about solving log equations a little bit more in depth. Who am I missing?
Oh wait, actually, I don't know what page was. Can you scribble them first? We are number 1 page.
It's calculator, right? Or is it not?
Oh.
No, I got it. Thank you. Where should I sit?
Open desk, open desk. Alright, so on page 349, we're going to take a look at these numbers 11 through 16 that we skipped yesterday. The majority of the properties that we've been practicing have been like the adding and multiplying property, the subtracting and dividing property, and kind of that power property that you can bring it out front. What we haven't really looked at is how how logarithms and exponentials are inverses of each other. They kind of technically cancel each other out in some instances. So that's what we're going to take a look at here. Okay? So just to refresh ourselves, I think I put the paper away, but if you take a look at 347, when we filled out these 5 different properties, if you look at number 3 and number 5, they were some instances where logarithms and exponentials can cancel each other out. Sometimes we're left with a power, sometimes we're left with an argument, okay, but as long as the base of the log matches the base of the exponential, those will cancel. So we're going to take a look at some of those instances, dealing with numbers at least, and maybe some variables for 11 through 16. So for instance, if you take a look at 11, notice how we have the natural log, and the argument is considered e to the 3x. What's the base of a natural log? E. So notice how the base of this logarithm matches the base of the exponential that's inside the argument. In that case, those are going to cancel, and we're just going to be left with 3x. What we can do is kind of confirm this if you wanted to play around with it a little bit on your calculator. Somebody pick a number for x for us. It could be anything you want. 2, 7, whatever. Okay, so natural log, and we'll do e. Let's say if we plug in 7 for x, our power would be 21. And when I hit enter, I get 21 as my answer. Notice how if I plugged in 7 for this x, I'd still get 21. So as long as the base of the log matches the base of the exponential, they're going to go away. Okay, they're inverses, they cancel each other out, and notice how we're just left with the power. Sometimes, though, we might have to be a little strategic. I'm going to skip 12 for a moment. Can we think about how 13 is very similar, but we might have to rewrite it somehow to help us? You see, Matt?
Could you rewrite and have e to the second power minus 3?
Not minus 3. It'd be 2 divided by 3.
Oh, yeah.
You're close.
Okay.
So we can rewrite a root as some type of fractional power. So just like square roots are a power of a half, a cubed root would be a power of a third, but notice how on the inside we have that additional power of 2. So this would be 2/3 as your power. So by rewriting it, notice how this setup is very similar to what we had in 11. The base of the log matches the base of the exponential, so those are going to cancel, and we're just left with 2/3. We doing okay so far? Okay. 14, kind of similar. Is there any type of property we can use to help us rewrite that logarithm? Kind of like how we had to rewrite 13. Can we rewrite 14 somehow? Maybe ignore that base of 10 to help you out. I'll cover it up. What do you think, Blair? There we go. Okay, so the number in front of a log, if we use a property, we can move it back as a power on the argument. Okay, so something like that. Now, what is the base of that logarithm? If you don't see it, it's understood to be 10. Notice how the base of that log is the same as the base of this exponential function. You have 10 to this power. So since the base of the log matches the base of the exponential, those cancel each other out, and we're just going to be left with x squared. Maybe we'll test this one. Maybe we'll use 7 again for x. So on my calculator, I can type in 10 to the power of 2 common log, okay, log base 10 of 7. And notice how I get 49. Isn't it true that if you plug in 7 in for this x and square it, you'll get 49? They're the same deal, okay? So as long as the base of the log matches the base of the exponential, they are technically inverses, they'll cancel, we're going to be left with, in this case, the argument. Okay. Now, what can be very, very tricky, and what I need us to understand here, is a slight difference in notation. Can you take a look at 12 and 15? What's the difference? Parentheses, right? Okay. So can you tell me what the argument is in 12 and what the argument is in 15? Yeah. It's only x. Okay, so sometimes you might see a natural or any log with parentheses. Sometimes you might not. If you see parentheses, that is a way of telling you that everything inside those parentheses is considered the argument. If you do not see the parentheses, the only argument is what immediately follows after that logarithm. So in this case, the plus 2 that's in this power for 15 is after the logarithm. Okay, it's like an addition of 2 after the fact. So this plus 2 is not a part of the argument. So let's kind of consider that difference for a moment. If we take a look at 12, notice how the base of e matches the base from the logarithm because it's a natural log. So in this case, these would cancel, and we're left with the argument of x plus 2. Maybe we'll verify it on our calculator. We'll use our answer, or our x value of 7. I can type in e to the power of natural log, and inside those parentheses, I'll type in 7 plus 2. If I hit enter, I get 9. Which is basically what we had as our solution. Okay, 7 plus 2 would give us that 9. Okay, what do you think is going to happen for 15? Do you think that this e and natural log are going to cancel and we're going to be left with x plus 2 again, like we were here? What do you think, Blair? Well, if this 2 was in front, then we could move it up and then it'd be squared. But we're adding it and not multiplying it. Okay? This is what's a little tricky. Okay? The fact that all of this was an argument means that those can cancel. But in this case, we have an addition of 2 after the argument. So it's not exactly the same notation. It's not the same setup. So we should probably anticipate that we're not going to get the same answer. Okay, let's try it. If I do natural or e to the natural log of 7, and then I close my parenthesis because only the x is my argument, I'm then going to add 2, okay, still in the power spot, and that's definitely not the same thing as 9. So there's something else going on here that's different than what 12 was kind of dealing with. Okay, I wonder if we can think about this. If we have the natural log of x in the power spot and we're adding 2 also in the power spot, can we think about a property of exponents? If you're adding 2 powers together, what were you doing before? Can we think about our properties of exponents? Yeah? Multiplying the bases. So this would have been e to the natural log of x times e squared. If you're adding powers, you were originally multiplying bases. So we can rewrite this expression using a property. Isn't it true if I'm multiplying the same base, I can add the powers? So if you check it, it should match what we started with. Now, since we broke up the powers in that fashion, now notice if we just take a look at this first exponential piece, this base of e matches this natural log base, and my argument is only x. So in this case, these would cancel, and we're just going to be left with x. On the other side, though, we have to multiply by e squared. So let's see if that matches what our calculator kind of told us before. If I take 7 times e squared, I get 51.7 whatever. Okay? So it's a little tricky. You have to be aware of what is considered the argument, and is the whole thing the argument, or is only a piece of it the argument? We have to be careful on the notation and understand how the expression is set up. Can we see the difference between the two? Those little parentheses make a world of a difference. We have to be a little careful. All right, let's see if we can try something similar for 16. Notice how 2 and this natural log base 5 are being added in the power spot. So if you're adding powers, you can use a property to break them up. You were originally multiplying the bases together. Maybe we'll type in the original problem just to see what happens. So I have 5 to the power of 2 plus, I need log base 5, so I'm going to do that math A option. And maybe I'll just keep using 7 for that x value. Okay, I get 175. Let's see if we can get the same thing after we simplify it. So I broke up those two powers. Since they were being added, I can multiply the bases. 5 squared is 25. And I have to multiply that by whatever this piece is going to simplify to. What do you think we're going to be left with? What do you think, Hadley? Why? That's good. This exponential base of 5 matches this log base of 5. So those are going to cancel, and we're going to be left with that x. So let's try it. If I do 25 times the 7 that I'm using to represent x, notice how I get the same 175. Okay, so we have to be, again, a little careful as to what's going on, in this case, in the power spot. Okay, if you're adding powers, you can separate them by multiplying the bases. So these were just a few examples of that inverse property, how they can cancel each other out. We're not necessarily going to use this a lot when we're solving. The other properties are going to be a little bit more useful, but notice how this property has its merit, because instead of dealing with, for instance, this complicated logarithm, I know I can just simplify it to 2/3. Or for instance, instead of having this complicated exponential, I can simplify it to x plus 2. Okay, so this property does have its merit in some cases. All right, did we finish the other 4 equations from yesterday? Yeah? Okay, so let's go ahead. We're going to start our next section on page 353. This whole section is going to be about solving exponential and logarithmic equations. We kind of already had our big toe dipped into this a little bit. Okay, when we did these 4 examples from yesterday, we kind of got our toes wet with solving equations, but we're going to do a little bit more today. We are going to save exponential equations for tomorrow. So since we're on this logarithmic train, I just want to keep that rolling. Let's go ahead and take a look at page 354. Okay, I want you to flip it to the other side. All All right, so we're going to start kind of towards the bottom here. We're going to jot down some thought processes that we can have in order to help us solve these logarithmic equations. And the ones that we were mostly doing yesterday, if I bring them up, notice how 17, 18, 19, and 20, all of these examples that we've already done had logarithms on both sides of the equations. So if we notice how that was a particular instance or pattern for these four of them, maybe we can jot down some of the strategies that we used yesterday to help us solve those. So in this second box, we're going to jot down some things we can do if we have logs on both sides. So maybe if you want to reference those from yesterday, you can, but can we think about perhaps a process that we used or some type of strategy that we used? I know they're not filled out on my paper, but maybe you can take a look back and see what we wrote down from yesterday. Can we think about what would be beneficial for us to do if we have multiple logarithms on both sides? Go ahead, Erica. Into one. Okay, so simplify multiple logs into one by using properties. Okay. I love it. If we can simplify the logarithms into one, that means we want one log on the left and one log on the right. Okay, if we have them everywhere, we're going to try to get one on the left, one on the right. So I'll say one on each side. So after we use the properties to our advantage to get one log on the left, one log on the right, where did we go from there? Can we take a look back? Yeah.
Just write whatever it is in the exponent or like equal to each other.
Okay, so there we go. We'll equal the arguments. Okay, after all, if these two logs are supposed to be equal, and we already have one log on the left and one log on the right, we already know the logs match because they should be the same. That means we can now check just the arguments to see when those are the same. So we'll equal the arguments. After we equal the arguments, what did we do? We're kind of summarizing our work from yesterday. Yeah?
Like, check to see if it's a solution or not.
Before we check it, okay, that's going to be our last thing. After we equal the arguments, but before we have to check it. How do you get that number that you have to check? What did we do? We solved for it. Okay, solve for the variable. Okay, so once we solve for the variable, then we're going to check it. Okay, we're going to write that down in the end. Okay, in the end, we're always going to check to see what? What do we have to check or what do we have to test? Yeah?
If it won't make an error.
What's going to cause it to make an error?
Negative number.
Negative or 0. Good. Okay, so in the end, always check to see if the argument is 0 or negative. If that's the case, it's going to be a no solution. Maybe I'll write that down in parentheses. No solution. All right, that's a fantastic summary of what we did yesterday, because all the ones we saw yesterday had logs on the left, logs on the right, and we basically used this same procedure for every single one of them, no matter what the numbers might have been. Sometimes, though, we're not going to have a log equation that has a log on the left and the log on the right. Sometimes we're just going to have one log in the entire equation itself. So this is going to be a little new for us because we haven't seen it yet, but I do want us to jot down, like we did before, some methods or some strategies that we can use if that's the case. So the first thing I want us to try to do, if we only have one logarithm, is to isolate it. That means get it all by itself. Move anything else in the equation to the other side. Okay, we're going to isolate the log, get it all by itself. Once we have the log all by itself, I want us to try to convert it to an exponential. Okay, we've done quite a bit of that, at least in the last section, where we were practicing going from logs to exponentials or exponentials to logs. Okay, we know that there's a conversion. We're going to use that to our advantage in this case. And then after we convert it, we're going to solve for the variable. And just like in the last case, after we solve it, we need to check it. Okay, so we're developing kind of a list of things that we can use, a strategy, a thought process, a method, depending on what kind of equation we might come across. Now let me ask you this. What if we can't do either of these? It's basically saying, what if you can't solve it by hand? Do we have like a last resort we can do? Yeah?
Both sides in the calculator are like crossing.
Their crossing point. Good. Graph to find the intersection. Okay. Remember when we were solving exponentials, and if we couldn't get the same base on either side, we had no choice but to graph it. We couldn't solve it by hand. Okay, we're going to do that same thing for logarithms if that's the case. Okay, for instance, if I have a natural log on the left and a common log on the right, those are different types of logs. They have different bases. So there's no way I'd be able to get them to be the same. So that's when I'm going to try to graph it to see where the intersection is. Okay, we might come across something like that. So now that we have this developed list, okay, kind of two things that we're going to be able to do by hand. One of them is a last resort on our calculator. We should be able to solve any logarithmic equation we come across. So let's see if we can do some of these. Let's take a look at the first example on the right. When I take a look at it, I notice how I have natural logs on the left and a natural log on the right. So this would probably be an example of where we have logs on both sides, kind of like the ones that we saw yesterday. So can we think about how we can simplify multiple logs into one log? That way I can get one log on the left and one log on the right. I actually already have only one log on the right. So is there any way I can change the two logs on the left into one log? Can we use a property? What do you think, Hadley? There we go. So I need x plus 2 times x. So that'd be x squared plus 2x. All right, we simplified. We're good to go. We have one log on the left, one log on the right. Next, we want to equal the arguments. Since we know the logs are already exactly the same, let's try to see when the arguments are exactly the same. So we equal the arguments. How do you want to solve for the variable? Can we think of a algebra technique or method we could use? I'm hoping there's something in that equation that shoots off a little light bulb in our head. Like, oh, I have to do this. We got a factor. Good. We have a quadratic. So in order to factor, let's go ahead and subtract that 8 over so it equals 0. Can we think of two numbers that multiply to -8 but add to 2? Good, Lainey? Positive 4, -2. All right, so our two answers are -4 and +2, but we have to check them to see if it causes an issue with our arguments. So if you were to plug these one at a time back in for the x's up top in the original equation, would they both work? Would one work? Would none of them work? Do either one of these cause an argument to be 0 or negative? Which one? -4. Okay, so we'll cross that out. We'll write no solution for that value. But if we plug in 2, both of those arguments would be positive, so that one works.
Thank you.
Thank you. So even though we got 2 answers, only one of them is considered a solution. Only one of them would actually work if you check it. Okay, so we have to be clear. Always check your work. Never a bad thing to do. All right, let's try a few more. We'll flip to the next page. Let's see. When I look at the first one, I see that I have 2 logs on the left and only the number 3 on the right. So this one's a little bit different because I don't have 2 logs or logs on the left and the right. Okay, I only have logs on one side. Can we perhaps use a property to condense these 2 logs into 1 log? They have the same base, so I most likely should be able to use a property. Go ahead, Caitlin. Divide them. Good. Okay, so x plus 2 over x minus 1. When you say them, I'm assuming you mean the arguments. Okay, divide the arguments, not the logs. Okay, divide the arguments. So this one's a little bit different because, like I said, we only have one logarithm. We don't have another log on the other side. So I want us to just take a look at what we said previously. Okay, if we only have one logarithm in our equation, we isolated the log. Notice how this log is all by itself on the left-hand side. It's not like we have a +4 or a -2, anything like that on the outside. So since it's isolated, I want us to see if we can convert this to an exponential. Can we think about these different parts of the log equation and how they might be rewritten to turn it into an exponential? Can we convert it? Let's maybe take baby steps. Out of all of these places, can we identify what the base is? 2? Okay, so if 2 is the base of the log, then 2 is going to be the base of your exponential. If this is a base of an exponential, we need to have some type of power on that 2, and then this exponential is going to equal something else. So the question is, out of the 2 remaining pieces, which piece is the power and which piece goes on the other side? What do you think, Hadley? There we go. Logs are powers. So if this log is 3, then the 3 is a power. So that would mean the argument is what this exponential piece equals. Okay, we're going to try to convert it. So in doing so, can we figure out 2 to the 3rd? That'd be 8. Can we solve from there? Yeah, let's go ahead and multiply the denominator over. Do a little algebra. Move some numbers. I got 10 over 7. All right, so there's an answer, but we have to check it. So if you were to take 10 over 7 and plug it in for the x's in the argument spots, would they both be positive? 10 over 7 plus 2, that's positive. 10 over 7 minus 1, that's positive. Okay, so this is a solution. All right. Let's take a look at the next one to the right. When you look at it, I see a natural log on the left, I see a natural log on the right. So I have a logarithm on both sides. What do you guys feel like doing from there? Do we have to use a property at all? Don't we already have one on the left and one on the right? Right? So if they're already done for us, one on the left and one on the right, where can we go from there? What do you think, Noah?
Well, they cancel out.
The natural logs cancel because we already know those are the same. So we're left with x plus 3 equals 2. So solving would give us -1. We got to check it. If you plug in -1 for the x in the argument, is it a positive argument? -1 plus 3, that's positive, right? Solution. All right, let's try the third one. When I look at it, I only see one logarithm. So what I'm going to try to do is isolate the log, get it all by itself, move anything else to the other side. So notice how this -3 on the end, I'm going to move it over by adding it, and that's going to give me a 4. Okay, get the logarithm all by itself if you only have one. Okay, so now that it's all by itself, can we convert it? Can we turn it into an exponential? Can we start with the base? What's our base? Good, Hadley? 3. Power? 4 equals? There we go. All right, so if we have one logarithm, we're going to try to convert it to an exponential to help in our solving process. Do we know what 3 to the 4th is? 81. Good. Okay, so add the 1, divide the 2. There's an answer, but we have to check it. If you plug in 41 into the argument spot, is it positive? Yep. So we got a solution. Do you guys think you can try the bottom 3? Maybe. Try it. See where you get. We'll check them in a little bit.
For this one,
No, that was just a smudge on that. So your interval is from 5 to 45. So you're going to use
so just the whole thing.
the whole thing, yeah. And
So I'm just like logging to it.
you can do that.
Just wants to.
It wants the whole thing, so break it up like you were
What
doing.
you bother?
If this said 22 to 35, you'd only do this. But this is
So
saying
just
5.
the same thing.
Yeah.
But That's not how you. Oh, that, I don't know. Multiply by reciprocal, so you only multiply that times 1 to the numerator, and then you get that, and then multiply 7 over 1 to the other side. I do not know. Blunder. Number 4. How have you done this? I got this. I got 2. Yeah. You're saying that they got no solution for that.
Because you did a stupid.
I don't know. I kind of. Yeah, that's what I
Minus
did.
5, minus 3, minus...
Yeah, I don't know.
Minus
I don't
2
know
and
the
5.
calculator. It's exact. It doesn't need to be screwed up. I just kind of like converted.
We're doing the quadratic formula.
And then I brought
Plug that
and
in.
then made it squared, and then I just solved it.
I am
Because whenever you make things exponential, right, I made this into because it's so 2 powers. That's it.
All right, guys. I know most of us are almost done, or we are done, but the bell's gonna ring in a little bit, so we'll go ahead and check these out tomorrow. Okay?
Trust me.